every day a chance to become the most beautiful day of your life. Good morning to one and all present here. On behalf of PG and Research Department of Mathematics, DG VAISHNAV College, I welcome all the PG students and CSIR aspirants. True prayer is neither a mere mental exercise nor a vocal performance. It is far deeper than that. It is a spiritual transaction with the creator of heaven and earth. Now, Tamuttal Vaku followed by college prayer.
நீராறும் கடலொடுத்த நிலமடந்து எழிலொழுகும் சீராரும் வதனமென திகழ்வரத கண்டமிது எக்கணமும் அதிசிறந்த திராவிடனல் திருநாளும் தக்க சிறு பிறை முதலும் தரித்தனரும் திலகமுமே அத்திலக வாசனை போல் அனைத்துலகும் இன்பமுற எத்திசையும் புகழ் மணக்க இருந்த பெரும் தமிழனங்கே தமிழனங்கே உன் சீரிழமை திறம் நிகழ்ந்து செயல் மறந்து வாழ்த்ததுமே வாழ்த்ததுமே வாழ்த்ததுமே
सत्यव्रतं सत्यपरं त्रिसत्यं सत्यस्य योनिं निहितं च सत्ये सत्यस्य सत्यं धृतसत्यनेत्रं सत्यात्मकं त्वां शरणं प्रपन्नाः वाणी गुणानुकथने श्रवणो कथायां हस्तौ च कर्मसु मनस्तव पादयोर्नः स्मृत्यां शिरस्तव निवास जगत्प्रणामे दृष्टिस्ततां दर्शनेस्तु भवत्तनूनाम् नमो भगवते तस्मै कृष्णायाद्भुतकर्मणे रूपनामविभेदेन जगत्क्रीडति यो यतः ॐ शान्ति शान्ति शान्तिः.
This is C4 workshop, Chase, Crack, Conquer, CSIR Net, which will make the CSIR aspirants to go to the next level. Today, our resource person is Mr. P. Thirumal, Assistant Professor, PG and Research Department of Mathematics, DG VAISHNAV College, Chennai. Now, I hand over the session to you, sir.
Good morning to all. I'm very happy to be a part of this C4 program. I thank the convener of C4 program, Professor R. Venkatramanan, Head, PG and Research Department of Mathematics, to give this opportunity for me. Okay, today we will discuss some problems on linear algebra. Okay, directly we'll go to the first problem. Okay, the first problem is, let V and U be vector spaces of the same dimension n. Let T is a linear map from V to U. Then the following options. First one is T is injective if and only if kernel of T equal to 0. Second option, T is injective if and only if T is surjective. Third is either A or B is true or last one is neither A nor B is true. So we have to check option A and B. Then we can answer directly C and D. Okay, we know the vector space, what is meant by space and dimension. So I don't know, no need to explain about the basic things. Okay, so directly we'll check the options. Okay, here linear map, we know the conditions of linear map. So T is a linear map, means T of x plus y equals to T of x plus T of y, and T of alpha times x equals to alpha times T of x, satisfying these two conditions. It's a linear map. Okay, we'll check the first condition. First condition is, if T is injective, if and only if kernel of T is 0. Okay, we will assume first T is injective, then check kernel of T is 0. And conversely, kernel of T is 0, then we will check T is injective or not. Okay, first I am taking kernel of T is 0. If kernel of T is 0, what is meant by a kernel here? Kernel of T equals to set of all points in V such that T of x equals to 0. That is collection of points such that T of x equal to 0. That is a kernel. We know the dimension of the kernel is nullity, and dimension of the image space is rank, and we know the rank nullity theorem also. Rank nullity theorem says that dimension of V, that is domain of the dimension, equals to rank of T plus nullity of T. Using that, we can prove this. Okay, I'm assuming kernel of T is 0. Then we need to show T is injective or not. Okay, injective map means T of x equals to T of, suppose T of x equals to T of y implies x equals to y. Then the map T is said to be injective map. So we have to check the image is same, means the points must be same. That is T of x equals to T of y implies x equals to y. We have to check this condition. Our assumption kernel of T equal to 0. That is kernel of T is a singleton set. Okay, just single point. Kernel of T is singleton set 0. Okay, let T of x equals to then T of x minus T of y equals to 0. T of x minus y equals to 0. This is by linearity. Our map T is a linear map. So we can T of x minus y equals to T of x minus T of y. So we can write T of x minus y equal to 0. By the definition of kernel, collection of point x belongs to be T of x equal to 0. Here T of x minus y equal to 0. So this implies x minus y belongs to kernel of T. So x minus y belongs to kernel of T means our kernel containing only one point, that is 0. So this implies x minus y. X minus y equal to 0. This implies x equals to y. So our assumption T of x equals to T of y implies x equals to y. So this map is injective map. So we are assuming kernel of T is 0. This implies T is injective. So this implies T is injective. Okay, next, suppose conversely, now assume that T is injective map. To prove the kernel of T is 0, we'll check this. Now assume that T is injective. Injective map means it's a 1-1 map, that is image T of x equals to T of y implies the points must be same, that is x equals to y. Okay, so that is our assumption is T of x equals to T of y implies x equals to y. This is our assumption. Now let a point x belongs to kernel of T. I am taking a point in kernel. So a point x belongs to kernel of T means this image must be 0. So T of x equal to 0. We know that the linear transformation, here T is a linear transformation. So T of 0 maps to the point 0. The 0 element mapped to the 0 element. So T of x equal to 0. Here 0 is an image of T of 0. This implies T of x equals to T of 0. Our assumption T is injective map. So injective map means T of x equals to T of 0 implies x equal to 0. So I am taking an arbitrary element x belongs to kernel of T. Then the point x equals to 0. So this implies kernel of T is a singleton set 0. So converse also true. T is injective implies kernel of T is 0. So the first option T is injective if and only if kernel of T equal to 0. The first option is true. Okay, now we'll check the second option. Second option, T is injective if and only if T is surjective. Okay, how to check this? T is injective if and only if T is surjective. We need to assume T is injective, then to prove T is surjective. Okay, we'll go to next page. Okay. Now I'm assuming T, let T be injective. I'm taking a point X belongs to kernel of T. So this implies T of X equal to 0. Already we did the same calculation. So T of X equal to 0, then T of 0, that is image, must be same. 0 element mapped to the 0 elements by the linearity property. So T of 0 equal to 0. So X belongs to kernel of T means T of X equals to T of 0. This implies T of X equals to T of 0. So inject by the injective property, again we have X equal to 0. So kernel of T, again singleton set. We know the nullity. Nullity means dimension of the kernel. That is a nullity. So nullity of T, our transformation nullity of T is 0 since kernel of T is singleton 0. And rank of T. Rank of T means dimension of the image space. Dimension of the image space is called the rank of T. Rank of T equals to dimension of V. This is equivalent to dimension of U. Since here nullity is 0. So by the rank nullity theorem, dimension of V equals to rank of T plus nullity of T. Here nullity is 0. So dimension of V equals to dimension of U. So this implies T of V equals to U. This implies the image is equivalent to U. So this that is T of V equivalent to U implies T is surjective. So injective implies T is surjective. Now conversely, suppose T is surjective, then what about T is injective or not? Now assume that T is surjective map. Surjective map means it's onto map. So onto map means the image T of V equivalent to U. Then that is image is equivalent to the codomain T of V equals to U. It's a surjective map. Then dimension of T of V equals to dimension of U. This is image is equivalent to U. So the dimension must be same. So dimension of T of V equals to dimension of U. Again, this is equivalent to dimension of V. This implies nullity 0. Nullity of the map is 0. Nullity is the kernel of T singleton 0. Nullity is 0. Then kernel must be singleton 0. Already we proved that kernel is singleton 0 means T is injective. T is a injective map. So we proved T is injective means T is surjective. If T is surjective means T is injective map. This is when U and V, dimension of U must be same as dimension of V. Codomain and domain must be have the same dimension. Then the linear map is injective means automatically it's a surjective map. It is a surjective map means it is injective map. Okay, so this here option B also correct. Okay, option C, either A or B is true. Here either A or B is true. Already we proved both the cases true. So this is not true. Neither A nor B is true. So this is also false. A and option B is true. That is in a vector space. T is a linear map from V to U be a linear map. Then injective map means a map is 1-to-1 or injective means the kernel is must be singleton 0. Or the kernel is singleton 0 means we can assume that the map is injective map, 1-1 map. Second option, T is injective. The map is injective map means automatically it's a surjective. It's a surjective map means we can assume automatically it's a injective map, both the case, if and only if. So take this as a property of linear linear map when the dimension must be same. The codomain dimension of V equals to n and dimension of E equals to n. Both same dimension means injective implies surjective, surjective implies injective. Okay, this is first question. Now we'll go to the second question. Okay, our second question. Let V and U be vector spaces of dimension m and n respectively. Now we have the different dimensions. The first example, same dimension, but here different dimension. Suppose m and V as a dimension m and dimension of the vector space U is n. Then T is a map from V to U, be a linear map. Then option A, B, C, D. First, suppose m is greater than n, implies T is not injective. We have to check these conditions. Okay, here, what about the option 3? Third option. First, we'll go to the third option. Since m equals to n, I'm taking m equals to n. The third option they given m equals to n. That is dimension of V and dimension of U equals to same. That is dimension of V. This is same as dimension of U. So both have the same dimension. So same dimension is already we proved in first example. Kernel of T equal to singleton, then T is an injective map. T is injective. Second option we proved T is injection means if and only if T is surjective map. So already we have kernel of T is singleton 0 implies T is injective. Injection implies T is injection if and only if surjection. So using this, we can prove m equals to n. Already we proved the same condition. If m equals to n, T is injective if and only if T is surjective. Already we proved this. So option C is true. Remaining we have to check. Now we'll check option A. Suppose m is greater than n. This implies T is not injective. We have to check. We have T of V contained in U. That is image is contained in the codomain. T of V contained in U. Then dimension of T of V less than or equals to n. Here n is the dimension of U. Okay. So dimension of T of V less than or equals to n. Our assumption n is less than m. N is less than m. So by the rank nullity theorem, we have nullity of T greater than 0. Since n is less than m, here m is the dimension of V. By rank nullity theorem, nullity of T plus dimension of T of V. This is the rank. So rank of T plus nullity of T equals to m. But we have n is less than m. So nullity of T is greater than 0. So nullity greater than 0 means kernel of T not equals to singleton set 0. Since our nullity is greater than 0, this implies kernel of T need not be a singleton 0. Kernel of T is singleton 0 means nullity is 0. But here nullity rank of the kernel, that is nullity, is greater than 0, strictly greater than 0. So kernel of T not a singleton set. So kernel of T not a singleton set means already we proved not injective. T is not injective. So injective map means the kernel must be a singleton set, and also conversely, kernel is a singleton set means T is a injective. But here kernel of T not a singleton set 0. This implies T is not injective. So first option is not correct. If m is less than n, T is not surjective. This is obvious. Here m is less than n, so we can prove rank of T less than or equals to m. Here m is less than n. This implies dimension of image space V. That is rank is this is less than here okay, here dimension of T of V less than dimension of U. So this implies T of V contained in U, that is strictly contained. T of V strictly contained in U. This implies T is not a surjective map. Since m is less than n, so here Option A is wrong. That is M greater than N means T is not injective. M less than N means T is not surjective. We proved that is image is strictly contained in U. So this is not surjective map. Option C, already the first question we proved. The domain and codomain have the same dimension. Then T is injective implies C is surjective. So the C is correct option. Okay. Now we'll go to third question. A third question. Let T be a linear transformation on a vector space V such that some conditions given. So T square minus T plus I equals to 0, where I is the identity matrix. Then T is singular, non-singular, invertible, not invertible. Singular means determinant 0. Determinant 0 means it's singular. T is non-singular, so determinant is non-zero. Invertible means inverse exists. Already we know that linear transformation means every linear transformation we can return as a matrix with respect to some basis. So if a linear transformation given means we have to check after changing the matrix, we can check the properties of linear transformation. That is also one type. Here we need to check using this condition. So what is the condition here? T square minus T plus I equal to 0. This is a given condition. Using this, we have to check the map T is singular or non-singular. First we will check singular or non-singular. Then we go to the invertible or not invertible. Okay. Okay, this is a given condition T plus I equal to 0. So this implies I'm taking I equals to what is the value? I equals to T minus T square. This is I. So this is equivalent to, I'm taking here T outside. So T remaining I minus T. So identity equals to T multiplied with I minus T. Okay, consider this is equation 1. Now we have T I minus T is I. So I'm taking this is the inverse of T. We can consider A inverse equals to I means, suppose AB equals to I means we can take A is the inverse of B or B is the inverse of A. AB equals to I. So here T I minus T equals to identity. So I'm considering I minus T is the inverse of T. So we'll check what about I minus T multiplied by T. So this is also I T minus T into T square. Identity matrix multiplied with this. Again this is T minus T square. Already we have T minus T square equals to I. Consider this is equation 2. Now from equation 1 and 2, T multiplied with I minus T equals to I minus T multiplied by T. Now consider I minus T equals to T inverse. Now we have T inverse equals to T inverse T. So this implies already these values are equal to I. LHS we have identity. T into I minus T is I minus T into T also I. So this implies T inverse equals to T inverse T equals to I. So inverse exists. T into T inverse equals to identity. T inverse into T equals to I. Inverse exists means what is the meaning of inverse exists? So this is invertible matrix. T is invertible. The linear transformation is invertible. Here inverse exists means what is the meaning of inverse exists means determinant is non-zero. Determinant non-zero means inverse exists. So determinant 0 means it's a singular, but here determinant is non-zero, then only the inverse exists. So here T is non-singular. Singular means determinant value 0, but here determinant is non-zero. Hence T is non-singular. Inverse exists. That is T inverse equals to T inverse T equals to identity. So T is a invertible matrix. Here linear transformation. That is every linear, we'll see in next some other problem. Every linear transformation can be written as a matrix with respect to some basis. Using standard basis, we will change the transformation into matrix. Okay, so in this problem, using this condition, we can answer. So T is a transformation satisfying this condition means that linear transformation is non-singular and invertible. Okay, now next problem. Okay. A be a real symmetric matrix and B is a given matrix I plus IA. Here I is the complex number, that is I square equals to -1, that is I is square root of -1. Here A is a real symmetric matrix. Then B is defined by B equals to I plus A. Then four options given. B is invertible if and only if A is invertible. Second option, all the eigenvalues of B are necessarily real. B minus I is necessarily invertible. Option D, B is necessarily invertible matrix. Okay, we'll check this four options. Okay, we know A is a real symmetric matrix. Real symmetric matrix always diagonalizable. This is, we know that. Real symmetric matrix are diagonal. But here B is defined by I plus, that is I is identity matrix, plus I times A. Okay, so we'll check the first condition. B is invertible if and only if A is invertible. I am taking arbitrarily some trial and error method. I am taking a matrix, a simple matrix 1, 1, 0, 0, 0. 1, 0, 0, 0. I am taking a matrix A. I'm taking A is 1, 0, 0, 0. The determinant is 0. So here A is not invertible, since the determinant is 0. Now I'm finding B equals to I plus IA. So what is our B is defined by I plus I times A. So I is identity matrix 1, 0, 0, 1 plus I times our matrix A is 1, 0, 0. So if you multiplying this I, so 1 plus I, 0, 0, this is 1 plus 0 is 1. So this is B. So first option, B is invertible if and only if A is invertible. This is if and only if. But I am taking a not invertible matrix. That is a singular matrix. I am taking a singular matrix, but my B is 1 plus I into 1. This determinant of B is non-zero. This determinant is 1 plus I into Y. Determinant is non-zero. So first option is not correct. I'm taking a singular matrix 1, 0, 0, 0. I'm taking 2 by 2. This is for simplicity. There is no dimension for this matrix. A be a real symmetric matrix. So I'm considering 2 by 2 matrix. For this singular matrix, I can find a non-singular matrix 1 plus I, 0, 1. This determinant is not 0. So first option is not correct. Okay, now we'll go to the option B. All the eigenvalues of B are necessarily real. Okay, consider the same B. What is here my B? 1 plus I, 0, 0, 1. This is my B. All the eigenvalues of B are necessarily real numbers. So how to find the eigenvalues? Eigenvalue means we need to find the characteristic polynomial. So determinant of B minus lambda I. This give the characteristic polynomial. Roots of the characteristic polynomial are called the eigenvalues. But we know the property. It is a diagonal matrix. So diagonal matrix or upper diagonal matrix or upper triangular matrix or lower triangular matrix, then the diagonal entries are the eigenvalues of the given matrix. So it's a diagonal matrix. So 1 plus I and 1. These are all the eigenvalues. So 1 plus I, 1 is the eigenvalue, but B is a complex value. But our option D says that all the eigenvalues of B are necessarily real. So need not be real. B has some complex eigenvalue also. So option B also not correct. Using the same example, we can skip option B also. Now, B minus I is necessarily invertible. So we'll check option C. That is B minus I is necessarily invertible. Invertible means non-singular matrix, then inverse exists. So what is B minus I? Okay, we have B equals to I plus IA, then B minus I equals to IA. This is by the condition. B is defined by I plus complex number I into A. So B minus I equals to IA. Okay, using same matrix, I am considering this 1, 0, 0, 1. This is since A is a real symmetric matrix. I am using, you can take any A, but A must be a symmetric matrix. Since this is our hypothesis, A be a real symmetric matrix, and we can define B using I plus IA, where I is identity matrix, I is a complex number. So I'm taking A is any matrix but real symmetric matrix. So 1 0 0 0. It's a real matrix, a real entries symmetric matrix. Okay, then what is IA? I 0 0 0. This is B minus I. In option C says that B minus I is necessarily invertible. Necessarily invertible means what is the determinant here? 0. So determinant of B minus I 0. So this is not invertible. So B minus I need not be invertible. That is, this is not invertible, singular matrix. So option B also not correct. So this is also not correct. So pending only C option, D. We have to check B is a necessarily invertible. So we have to check this condition. B is necessarily invertible. B is invertible. So given condition, what is the condition they given? B equals to I plus IA. Okay. So B equals to I plus IA. Okay, we know that if X is a eigenvalue of A corresponding to some eigenvalue lambda. Sorry. Okay, this is, we need to prove B is invertible. Suppose X is an eigenvector of A with respect to some eigenvalue lambda, then AX equals to lambda X. This is, we know that AX equal to lambda X. Okay, for B, I'm considering B into X. What is B? B is I plus IA. So I plus IA into X. Just I'm replacing B by definition, I plus IA. Okay, this is equivalent to IX plus IA into X. I'm interchanging this IX plus this constant. So IAX. So IX plus I times AX. AX, we know that if X is an eigenvector of a matrix A with respect to some eigenvalue lambda means AX equal to lambda X. So I'm replacing AX to lambda X. Here I'm taking X common. So remaining I plus I lambda. Okay, here now we have Bx I plus I lambda into X. I'm taking X is the eigenvector for B with respect to the eigenvalue I plus I lambda. So I plus I lambda, where lambda belongs to any real number. For any lambda value, sorry, this is 1. So Bx equals to 1 plus, this is Ix is X. So Bx equals to X plus I times lambda X. I'm taking X is outside, then 1 plus I lambda into X. Now we have Bx equals to 1 plus I lambda into X. So now this is 1 plus I lambda is the eigenvalue. Is the eigenvalue of B. For any lambda value, this is non-zero. So all the eigenvalues are non-zero eigenvalues. Eigenvalues are non-zero. We know product of the eigenvalues equals to determinant of the matrix. So product of the eigenvalue equal to determinant of the matrix. But product of the eigenvalues, all the eigenvalues are non-zero, then the product must be non-zero. This implies determinant of B is non-zero. Determinant of B is non-zero means B is invertible. So fourth option is correct. So using this we can prove Bx equals to I plus Ia into X. I'm replacing Ax equals to lambda X. Since A is a real symmetric matrix is always diagonalizable matrix. So Ax equals to lambda X for A is eigenvector of A with respect to the eigenvalue lambda. So I'm replacing Ax equals to lambda X. From this we can conclude 1 plus I lambda is the eigenvalue of B. This is a non-zero value. If you give any lambda value, lambda is real, any real number, this is not zero. Here 1 is the real part is non-zero. So eigenvalue is always non-zero. So eigenvalue are also non-zero. Product of the eigenvalue equivalent to the determinant of the matrix. So determinant of B is non-zero. This implies B is invertible. Okay, now option D is correct. So using this, no need to take the same example. You can take any A, but A must be a real symmetric matrix. Symmetric matrix with real entries. You can take any matrix, but I'm taking this is 1 0 0 0. It's a simple matrix. Using this, we can omit option A is not correct. Option B is also not correct. Option C is also not correct. B is necessarily invertible matrix. Okay, so only one option is correct. D is correct option. Now we go to the fifth problem. Okay, let A be a 2 by 2 matrix over R. Okay, this is 2 by 2 matrix with real entries. They given the condition determinant of A plus I equals to 1 plus determinant of A. Then we can conclude determinant of A. What about the determinant of A is 0, or the matrix must be 0, or trace of A is 0, or A is non-singular. We have to check this condition. So the given condition is determinant of A plus I equals to 1 plus determinant of A. Here A is a 2 by 2 matrix. So I am considering A is some 2 by 2 matrix, arbitrary matrix A, B, C, D, where A, B, C, D are real numbers. A, B, C, D from real numbers. Then what is A plus I? A plus I is A plus 1, B, C, D plus 1. This is A plus I matrix. Okay, the condition, given condition is 1 plus determinant of A equals to determinant of A plus I. That is determinant of A plus I. What is determinant of A plus I? Just determinant 2 by 2 matrix. The determinant is A plus 1 multiplied with B1 minus BC. This is equivalent to right side 1 plus determinant of A. Determinant of A is AD minus BC. Okay, now we can simplify this. AD plus A plus D plus 1 equals to 1 plus AD minus BC. Okay, AD cancelled. So remaining, I think I made a mistake. Okay. This is AD plus A plus D plus 1 minus BC equals to 1 plus AD minus BC. Now AD cancel, minus BC cancel. Now we have A plus D plus 1 equals to 1. Okay, this is 1 also cancel. So A plus D equal to 0. So we have A plus D equal to 0. So I'm taking A is a 2 by 2 matrix with real entries. I'm applying this condition. Determinant of A plus I equals to 1 plus determinant of A. Finally, I arrived at the condition A plus D equal to 0. Here, what is A plus D? Diagonal entries, A plus D. So A plus D, sum of the diagonal entries is called the trace. Trace of A. Trace of A means sum of the diagonal entries. So sum of the diagonal entries A plus D is 0. So trace of A is 0. So from this condition, we can conclude trace of A equal to 0. We cannot say about determinant of A and A non 0, A is non-singular. We can conclude using this condition, trace is 0. So A plus D equal to 0. So in a 2 by 2 real matrix, determinant of A plus I equals to 1 plus determinant of A means trace of A is 0. So this is the correct option. Okay. Now sixth question. The trace of the, okay, this is very simple one. Consider this is a matrix A. A matrix is 2 1 0 0 2 0 0 0 3 whole power 20. So trace, suppose A is 2 1 0 0 2 0 0 0 3 means this is a trace means just now I told trace means sum of the diagonal entries. Sum of the diagonal elements equals to trace. Trace of A. So just 4 plus 3 7. 7 is the trace of A. But here whole power 20. We have a property, if lambda is the eigenvalue of A, then lambda square is the eigenvalue of A square. Lambda cube is the eigenvalue of A power 3. So lambda power 20 is the eigenvalue of A power 20. So eigenvalues. So this matrix eigenvalues we can find easily. Eigenvalues of A. Eigenvalues of A is, here my A is 2 3 0, means I'm considering this is A dash, the matrix A dash. Eigenvalues of A is 2 2 3, since it's a upper triangular matrix. In upper triangular matrix or lower triangular matrix or a diagonal matrix, the diagonal entries are the eigenvalues. So here eigenvalues are 2 2 3 are the eigenvalues of A. This matrix eigenvalues 2 2 3, this diagonal entries are the eigenvalues. For this matrix A power 20, we have a property lambda is eigenvalue of A, means then lambda square is eigenvalue of A square, lambda cube is the eigenvalue of A power 3. Similarly, lambda power n is the eigenvalue of A power n for any positive integer. So A dash eigenvalues are 2 power 20, 2 power 20, 20. This is the eigenvalues. We need to find the trace. We have some properties. Product of the eigenvalue equals to determinant of the matrix. Product of the eigenvalues of a matrix A equals to product of determinant. Next, sum of the eigenvalues. Sum of the eigenvalues of A equals to trace of the matrix A. We have this property. Okay, so here we need trace. So sum of the eigenvalues equivalent to the trace. So sum of the eigenvalues. So we have the eigenvalues. It's a 3 by 3 matrix. So it has 3 eigenvalues. So 2 power 20 plus 2 power 20 plus 3 power 20. So if you are adding, this is okay. This is 2 power 20 is common. So 2 times 2 power 20 plus 3 power. So this option C is correct. Okay, 2 into 2 power 20 plus 3 power 20 is the trace of the matrix. So this is very simple. Using this property we can identify easily. I think this is 3 mark question in some CSIR exam. No need to calculate this. We know the property. This is lambda power n is the eigenvalue of A power n. Using this, just write the eigenvalues. 2 power 20, 2 power 20, 3 power 20 is the eigenvalues. We know that sum of the eigenvalue equals to trace of A. So we need to find the trace value. So just take the sum value, and C is the correct option. Okay, now 7th question. Okay, let P of x equal to a0 plus a1x plus a2x square plus etc. an x power n be a non-constant polynomial of degree n greater than or equals to 1. Okay, here degree is greater than or equals to 1. It's a non-constant polynomial. So P of x is given. P of x equals to a0 plus a1x plus x square plus etc. plus an x power n. And consider the polynomials q of x and r of x. There are 2 polynomials. Q of x is defined by integral 0 to x p of t dt, and r of x is defined by derivative of the polynomial p of x. Now let V denotes the real vector space of all polynomials in X. We know that the set of all polynomials in form a vector space. So V denotes the real vector space of all polynomials in X. Then which of the following are true? Q and R are linearly independent in V. So we have to check Q and R linearly independent. Second option, Q and R are linearly dependent. So if you check any one condition, this is enough for A and B. Third option, x power n belongs to the linear span of Q and R. Third one, x power n plus 1 belongs to the linear span of Q and R. We have to check this 4 options. So first, we need to find what is Q and R. So this is a polynomial. Given polynomial P of x equal to a0 plus a1x x power n. Q of x is defined by 0 to x P of t. So what is P of x is the P of x defined by like this. So P of t, what is P of t? a0 plus a1t plus a2t square plus etc. plus an t power n. This is P of t. So dt. So after integrating, this is a0 t plus a1 t square by 2 plus a2 t cube by 3 plus etc. plus an t power n plus 1 by n plus 1. Okay, after substituting lower limit 0, upper limit x. Okay, if you substitute 0, all the terms 0, so just replacing t by x. So a0x plus a1 x square by 2 plus a2 x cube by 3 plus etc. plus an x power n plus 1 by n plus 1. So this is q of x. Now what is r of x? R is defined by derivative of p of x. Take the derivative of p of x. So a0 is constant, so 0. So a1, sorry. So a1 plus 2a2x plus 3a3x square plus etc. plus n an x power n minus 1. Okay, so this is r of x. So q of x is a polynomial of degree n plus 1. R of x is a polynomial of degree n minus 1. Here n is greater than or equals to 1. Now q and r are linearly dependent in V. So linearly independent means r of x and q of x cannot be a linear combination of some constant alpha. So linearly dependent means r of x, the polynomial r of x can be written as some constant multiple of q of x. Then r and q is said to be linearly dependent. But first, q and r are linearly independent. Suppose linearly dependent means just constant multiples. R of x can be written as alpha times qx or q of x equals to 1 by alpha times r of x. But our q is degree n plus 1, polynomial of degree n plus 1, but r is polynomial of degree n minus 1. So it cannot be linearly dependent. It cannot be written as constant multiple of q of x or q of x equal to some constant multiple of r of x. We cannot write like this. Since its degree is n plus 1, r of x degree is n minus 1. So it cannot be linearly dependent. So option B is not correct. So q and r are linearly independent in V. Both are linearly independent vectors. So r and q are both are independent vectors. Reason is this is degree is n plus 1, here degree is n minus 1. We cannot written as a linearly dependent means it's a constant multiple of q of x. That is r of x is some constant multiple of q of x. We cannot be written like this. So q and r are linearly dependent is not correct. So this is linearly independent. Okay, next we have to check x power n belongs to the linear span of q and r. Okay, linear span. So x power n is a linear span of q and r of x. So linear span means some alpha times q of x plus some beta times r of x. X power n, this is third option. X power n equals to alpha times q of x plus beta times r of x. Okay, actually this is very simple calculation. I leave it to the exercise. So that is linear span means x power n, the polynomial. Actually, V denotes a real vector space of all polynomials in X. So I am taking x power n is one polynomial. This polynomial is a linear span of alpha times q of x plus beta r of x. So alpha times, substitute here q of x value. What is our q of x? We calculated a0x plus a1 x square by 2. I think it's correct. A1 x square by 2. Okay, a1 x square by 2, a2 x cube by 3 plus a2 x cube by 3 plus etc. Beta times r of x. What is r of x? That is derivative a1 2a2x, a1 2a2, sorry, a1 plus 2a2x plus etc. Okay, write this properly. Okay, x power n. So just expand this, just multiply alpha with this and beta with this. Then LHS we have x power n, right side we have a polynomial. This is up to x power n plus 1. This is up to x power n minus 1. Just equating the coefficients. Equating the coefficients of n plus 1 and constant term. I didn't write properly here. So just I am saying the idea. X power n is a linear span means linear span of q of x and r of x means x power n can be written as alpha times q of x plus beta times r of x. So here just substitute q of x value and R of x value. Just expand this, then equating the coefficient of x power n plus 1 and constant value, you will get alpha equal to 0 and beta equal to 0. Both the value you will get 0. Then what is the meaning? X power n not a linear span of q of x and r of x. So option C is not correct. That is, x power n belongs to the linear span of q and r, but we cannot write is a linear span. At least one alpha or beta is non-zero, but you will get both the values 0. Alpha is 0 and beta is 0. Do this calculation, simple calculation. Just multiply with alpha, multiply with beta, and add the like terms, x coefficient, x square coefficient, up to here x power n plus 1, here x power n minus 1. Like the add the like terms and equate the coefficient of x power n plus 1 and constant term, you will get alpha is 0, beta is 0. Both the values are 0. So x power n does not belongs to the linear span of q and r. So this is not correct. Similarly, x power n plus 1. So x power n plus 1 belongs to the linear span of q of x and r of x, means it is some constant multiple of q of x plus beta times r of x. Similarly, substitute the values and equating the coefficient of x power n plus 1 and constant term, you will get again alpha value 0, beta value 0. For this problem also, you will get this alpha 0, beta 0. That is, x power n plus 1 does not belongs to the linear span of q of x and r of x. Since you will get alpha value 0, beta value 0. This is simple calculation, so you can do. So in this, q and r are linearly independent in V. This is correct. So linearly dependent, this is also not correct. X power n does not belongs to the linear span of q and r. X power n plus 1 also does not belongs to the linear span of q and r. I didn't this fully. You can do. This is very simple. I say the idea. Both the alpha value, beta value 0. In the x power n plus 1 also, you will get alpha value 0, beta value 0. Okay. Now we'll go to the next problem. 8th problem. Which of the following matrices is or not diagonalizable? Okay, 4 matrices given. So we have to check matrix diagonalizable or not. What is meant by a diagonalizable? A matrix is diagonalizable means a matrix A is said to be diagonalizable matrix. There exists a matrix P, invertible matrix P, such that P inverse AP equals to D. If A is said to be a diagonal matrix, means there exists a invertible matrix P such that P inverse AP equals to D, where D is a diagonal matrix. That diagonal eigenvalues. If n cross n matrix, it diagonal entries containing the eigenvalues P inverse AP. Here, that is invertible matrix. P is invertible matrix, so inverse exists. P inverse AP equals to diagonal entries. This is, we know what is the mean by a diagonalizable. A matrix is diagonalizable. It has some properties. Already in one problem we say that real symmetric matrices are diagonalizable. So there exists a matrix P, but for real symmetric matrix, this P is always orthogonal matrix. There exists an orthogonal matrix P such that P inverse AP equals to D for real symmetric matrix, that is orthogonally diagonalizable. Real symmetric matrix, that is another property for real symmetric matrix. Okay, now we'll check here just diagonalizable. Which of the following matrices are diagonalizable? So diagonalizable means there exists an invertible matrix P such that P inverse AP equals to diagonal matrix. This diagonal elements only the eigenvalues. Okay, option A. Okay, before that we'll see some results. If the algebraic and geometric multiplicity of each eigenvalues are equal, then it's a diagonalizable matrix. Okay, what is meant by the algebraic multiplicity and geometric multiplicity? So algebraic multiplicity of an eigenvalue means how many times it is repeated. So suppose some eigenvalues 2, 2, 3, 3, 2 means algebraic multiplicity of 2 is 3. It is repeated 3 times. So algebraic multiplicity of 2 is 3. Geometric multiplicity means number of linearly independent, okay, I will write number of linearly independent eigenvectors with respect to the eigenvalue lambda. That is a geometric multiplicity of an eigenvalue lambda. That is number of linearly independent eigenvectors corresponding to the eigenvalue lambda. So how many linearly independent vectors exist? The corresponding lambda. That is the geometric multiplicity of the eigenvalue. So a matrix is diagonalizable means geometric multiplicity equals to algebraic multiplicity for every eigenvalue, then the matrix is diagonalizable. This is first property. Second property, geometric multiplicity always less than or equal to arithmetic multiplicity. Sorry, algebraic multiplicity. So algebraic multiplicity 1 means no need to calculate geometric multiplicity. Always this is also 1, not always greater than 1. So GM is less than or equals to AM. So if you know the arithmetic multiplicity 1 means geometric multiplicity you can consider 1. So no need to calculate that part. Okay. If the matrix has distinct eigenvalues, then it is diagonalizable matrix. This is another property. Not only this property, using minimal polynomial and nullity of the null space, dimension of the null space, we have many properties to check the diagonalizable. In this problem, this is enough. Okay. So first to check 2, 0, 1, 0, 3, 0, 0, 2. It's diagonalizable or not. Okay. So given matrix A equals to 2, 0, 1, 0, 3, 0. 2, 0, 1, 0, 3, 0, 0, 0, 2. 0, 0, 2. Okay. This is my matrix A. We have to check it is diagonalizable or not. So first eigenvalues. What are the eigenvalues? It's a upper triangular matrix. So 2, 3, 2. That's diagonal entries are the eigenvalues. Eigenvalues 2, 3, 2 are the eigenvalues. So arithmetic multiplicity of 2 is 2. 2 times it is repeated. So arithmetic multiplicity of 2 is 2. Sorry, algebraic multiplicity, not arithmetic multiplicity. Algebraic multiplicity of 2 is 2. Now to calculate geometric multiplicity. Here algebraic multiplicity of 3 is 1. Since it is repeated only 1 time, so geometric multiplicity also 1. That is always less than or equal to this value. So this is equal for the matrix for the eigenvalue lambda equals to 3. Algebraic multiplicity equals to geometric multiplicity. We have to check for the lambda value 2. For lambda equals to 2, we have to check the geometric multiplicity. So algebraic multiplicity is 2. Algebraic multiplicity 2. We have to check the geometric multiplicity. So what is the definition of geometric multiplicity? Number of linearly independent eigenvectors corresponding to the eigenvalue lambda. Here eigenvalue is 2. For lambda equals to 2, we need to find the number of linearly independent eigenvectors. Okay, how to check? A minus lambda I into x equals to 0. Okay, this implies lambda value is 2. 2i into x equals to 0. So a minus 2i. So what is a minus 2i here? 0, 0, 1, 0. 3 minus 2 is 1. Again 0. 0. This is 1. This is 0. 0, 0. 0. What is this? Wait. Sorry, this is not responding. 1 minute. Okay. Now, A 0, 0, 1, 0, 1, 0. Last entry 2 minus 2 is 0. So 0, 0, 0. So this is 0. Consider this is x1, x2, x3 equals to 0, 0, 0. So from this first row, first column, if you multiply, you will get x3 equal to 0. Second, x2 equal to 0. x3 0, 0. So x1 any real number. So the vector x equals to x1, x2, x3. x1 can be any real number, x2 0, x3 value 0. So this implies v equals to 1, 0, 0. We can write it x into 1, 0, 0. So only one linearly independent eigenvector corresponding to the lambda value 2. So here only one vector exists, remaining 0, x2 value 0. Only x1 take any value. So x equals to x0, 0. It can be written as x into 1, 0, 0. So 1, 0, 0, 0. This is our vector. Only one vector exists. So geometric multiplicity for lambda equals to 2. Algebraic multiplicity is 2. Geometric multiplicity 1. So AM not equals to GM. This implies not diagonalizable. So first one, this matrix is not diagonalizable. Second, B, 1, 1, 1, 1. I think more space. Okay, we'll do here. Okay. Okay, this is very simple. I'm doing here 1, 1, 1, 1. So we need to find the determinant. What is the determinant? Determinant of A minus lambda I. I'm finding the characteristic polynomial. So determinant of A minus lambda I will give this is 1 minus lambda, 1 minus lambda, 1, 1, 1 minus lambda. Take the determinant. What is the determinant here? 1 minus lambda the whole square minus 1 equal to 0. So expanding 1 plus lambda square minus 2 lambda minus 1 equal to 0. So lambda square minus 2 lambda equal to 0. So take lambda outside. So it becomes lambda minus 2 equal to 0. So for the second problem, lambda equal to 0, lambda equal to 2. For the second problem, lambda equals to 0, lambda equals to 2. It's a 2 by 2 matrix. So characteristic polynomial of degree 2. So it has two roots, lambda equal to 0, lambda equals to 2. If the matrix has distinct eigenvalues, then it is a diagonalizable matrix. So option B is a diagonalizable matrix. The eigenvalues are distinct eigenvalues. 0 and 2 are the eigenvalues. It has a distinct eigenvalue, so it is a diagonalizable matrix. Okay, now for the matrix C, 2, 1, 0, 0, 3, 0, 0, 0, 3. We have to check this. No space here. Okay, we'll include one more slide. Okay, now we have to check the matrix C, 2, 1, 0, 0, 3, 0. Okay, now I'm taking A is a matrix, 2, 1, 0, 0, 3, 0, 0, 0, 3. This is my matrix. I will return again, 2, 1, 0, 0, 3, 0, 0, 0, 3. Okay, so for this matrix, again, we have to check it is diagonalizable or not. Eigenvalues, lambda 1 equals to 2, lambda 2 equals to 3, lambda 3 equals to 3. It has 3 eigenvalues. Since it's a 3 by 3 matrix, upper triangular matrix, so diagonal entries are the eigenvalues. So 2, 3, 3. Okay, so lambda 1 equals to 2. For this, algebraic multiplicity 1. So geometric multiplicity also 1. This is less than or equal to geometric multiplicity, always less than or equals to this value. So this 1. So GM AM equals to 1. So for the lambda value 3. For lambda equals to 3, consider lambda equals to 3. Algebraic multiplicity is 2. We need to find the geometric multiplicity. Suppose geometric multiplicity is 2 means it is diagonalizable. 1 means not diagonalizable. We have to check the geometric multiplicity. How to check the geometric multiplicity? A minus lambda I into x equal to 0. From this, I'm taking directly here lambda value is 3. If you substitute 3, what will get? Minus 1, 1, 0, 0, 3 minus 3 is 0, 0, and 0, 0. This value is again 3 minus 3 is 0. Multiplied by x, y, z equals to 0, 0, 0. From this first row, first column, if you multiply minus equal to 0. Next, all the entries are 0. So y can take any value and z belongs to R. So, but not any value. Here relation x minus x plus y equal to 0. This implies x equals to y. Z belongs to R. You can take z any value. So what is the relation here? This can be written as so x into 1 1 0 plus z 0 0 1. Here x and y the same value. So I'm taking x value 1 means y value 1. So I'm taking x outside. That is x y. I'm replacing 1 x x. So taking x outside. So 1 1 0 plus z 0 0 1. So the eigenvector, distinct eigenvectors 1 1 0 0 0 1. Two linearly independent eigenvectors exist for this lambda value 3. So geometric multiplicity is also 2. Number of linearly independent eigenvectors 2. There exist 2 linearly independent eigenvectors. So geometric multiplicity is 2. Algebraic multiplicity is also 2. So both the value equal. For the lambda value 2 is also equal, lambda value 3 is also equal. Hence the matrix is diagonalizable matrix. So here third is diagonalizable matrix. Now fourth one, 1 minus 1 2 4. So 1 minus 1 2 4. This is a 2 by 2 matrix. You can find the using a characteristic polynomial. Find the roots. What is the roots here? Okay, lambda value 2, lambda value 3. I have the answer. Or just you can calculate, very easy. Just a determinant of a minus lambda I equal to 0. This will give the characteristic polynomial. Roots of the characteristic polynomial is lambda equals to 2, lambda equal to 3. This is distinct eigenvalues. So distinct eigenvalue means it is diagonalizable matrix. So fourth is diagonalizable. That is very simple calculation you can do. Okay, so in this here algebraic multiplicity not equal to geometric multiplicity for one lambda value. So this is not diagonalizable. This is distinct eigenvalue, so it is diagonalizable. C using this condition, that is algebraic multiplicity, geometric multiplicity same for all the eigenvalues. So this is diagonalizable. Fourth one is distinct eigenvalue, so it is diagonalizable. So already I said diagonalizable means this matrix 1 minus 1 2 4. This matrix multiplied with some matrix P and matrix P inverse. Invertible matrix. There exists an invertible matrix P equals to diagonal matrix. This diagonal matrix containing the 2 3 or 3 2. Then the matrix is diagonalizable. This is the meaning. There exists a matrix P such that P A P inverse equals to D, diagonal matrix. Thus diagonal entries eigenvalues 2 3. So we can diagonalizable the matrix 1 minus 1 2 4. So this is a diagonalizable matrix. Okay, next 9th question. T is a linear transformation R3 to R power 4. It's a linear transformation. The image value is given. So image of 1 0 1 1 0 1 0 1 0 1 1. This image value given R3 to R power 4. So 3 tuple to codomain is 4 tuple R power 4. Then what is the image of 1 1 1? They are asking the image of 1 1 1. So how to calculate this image? Okay, first check it's R3. R3. So dimension is 3. So they given 3 vectors value. So 1 1 1 0 1 0 1 1. First calculate the determinant. This is not 0. So it's a basis for R3. That is 1 1 0 1 0 1 0 1 1 is a basis for R3. These 3 vectors are linearly independent vectors. Determinant is non-zero. This is enough to calculate. So these 3 vectors is a basis for R3. The standard basis is 1 0 0 0 1 0 0 0 1. This is a standard basis for R3. But here linearly any 3 linearly independent vectors form a basis. So 1 1 0 1 0 1 0 1 1. It's a linearly independent vector. So it's form a basis for R3. So basis element image is given 110, 2000, 101. Its image is 2, 4, 0, 0, 011. Its image is given. So now we have basis. Basis means every element in R3 can be written as a linear combination of basis element. So 111. Here we have 110. Okay. So this is a basis element. So 1, 1, 1. It can be written as linear combination of this basis element. So x times 1, 1, 0 plus some y times 1, 0, 1 plus z times 0, 1, 1. This is a basis element. So every element in R3 can be written as a linear combination of the basis element. Then only it's a basis. Okay. Now from this, we can add these terms. So this is x plus y, next x plus z, last one y plus z. Okay, 0. This is y plus z. Okay, y plus z. So this is 1, 1, 1. So this is x plus y equals to 1, x plus z equals to 1, y plus z equals to 1. We need to find x, y, z values. How to find x, y, z values here? Okay, okay, x plus y equals to 1, x plus z equals to 1. So y plus z equals to 1. Add all the equations. You will get 2x plus 2y plus 2z equals to 3. Okay. Now x plus y plus z equals to 3 by 2. From equation 1, x plus y equals to 1. So what is the value here? Y equals to 1 minus x. Here z equals to 1 minus x. So substitute here, you will get z equals to 3 by 2 minus x plus y. So 3 by 2 minus x plus y value is 1. So 3 by 2 minus 1 is 1 by 2. So z value 1 by 2. So z value 1 by 2 means value again 1 by 2. What is y value? Again 1 by 2. Since x plus y equals to 1, x plus z equals to 1. We found z equals to 1 by 2. So x equals to 1 by 2, y equal to 1 by 2. Now we find the value, x value, y value, z value. So now 1, 1, is a linear combination of 1 by 2, 1, 1, 0 plus 1 by 2, 1, 0, 1 plus 1 by 2, 0, 1, 1. Okay. This is simple calculation. Okay, now 1, 1 can be written as a linear combination of the basis vector 1 by 2, 1 by 2, 1 by 2. Now we need to find the image of this 1, 1. So T of 1, 1. We need to find this image. This is question T of 1, 1. So T of this 1, 1 is a linear combination of this value, that is 1, 1, 0 plus 1 by 2, 1, 0, 1 plus 1 by 2, 0, 1, 1. This is a linear transformation, so we can outside take 1 by 2 is outside, that is t times alpha x equals to alpha times t of x. This is a linear transformation property, x plus y equals to t of x plus t of y. Using this property, 1 by 2, then t of 1, 1, 0. What is the value? Image of t of 1, 1, 0 is, they given the value 2, 0, 0, 0 plus t of t 1, 0, 1 value 2, 4, 0, 0 plus image of 0, 1, 1 value is 0, 0, 2, 0. Now this is 1 by 2, just coordinate wise addition. What is the value here? 2 plus 2, 4, comma, next 0, 0, 2, remaining 0. All the coordinate values 0. Okay. Sorry, I will write again this. Okay. So this is 1 by 2 times 4, 4, 2, 0. So this is equivalent to 2, 2, 1, 0. This is the image of 1, 1, 1. So in this option, C, 2, 2, 1, 0. So C is the correct option. So using This is a linear transformation. They said it's a linear transformation, so we can use the linear transformation property. This is a linear transformation, means it's satisfying these two conditions: t of x plus y equals to t of x plus t of y, t of alpha times x equals to alpha times t of x. Okay, the image values, three image values given: 1 comma 1 comma 0, 1 comma 0 comma 1, 0 comma 1 comma 1. This three form a basis for R3. So every element can be written as a linear combination of the basis element. So I'm writing the linear combination of the basis element. So first I found the value of x, y, z, all the values 1 by 2, 1 by 2, 1 by 2. Then use this image values for the linear transformation value. Without knowing the linear transformation, we can find the value of t of 1 comma 1 comma 1, that is 2 comma 2 comma 1 comma 0. Okay. Option C is correct. Now we'll go to the 10th problem. Okay, here n is a positive integer and Hn be the space of all n cross n matrices A. So A is a n cross n matrices with entries in R. So real n cross n matrices with entries in real, satisfying some condition Aij equals to ARS whenever I plus j equals to R plus S. For I, j, RS equals to 1 to up to n, then the dimension of Hn as a vector space over R. So we need to find the dimension of Hn. What is Hn here? Collection of matrix Aij, where Aij equals to ARS. Where what is the relation between Ij and RS? I plus j equals to R plus S. That is Ij place value I plus j equals to R plus S. So first write this matrix. So A11, A12, A13, A1n. So second row, first entry, second row, second column, second row, third column, up to A2n, A31, A32, A33, up to A3n. So nth row, an first column, an2, an3, up to nth row, n column. So this is n cross n matrix. Sorry. So in this n cross n matrix, they given some condition Aij equals to ARS. So A12 equals to A21. Since 1 plus 2 is 3, 2 plus 1 is 3. So these two entries are same. A12, A21 is same. So these two entries are same entries. Okay, suppose what about A13? 1 plus 3 is 4. So A22, next A31. So 1 plus 3 is 4, 2 plus 2 is 4, 3 plus 1 is 4. That is the place Aij equals to ARS. Whenever these entries are equal, I plus j is equal to R plus S. Then these two entries are equal. Here 1 plus 3 is 4, 2 plus 2 is 4, 3 plus 1 is 4. So this all the entries are equal value. So A13, A22, A31. So A13, A22, A31. This is equal value. Next, suppose here 41, A41, 4 plus 1, 5, 3 plus 2 is 5, 2 plus 3 is 5. Here A14, 1 plus 4 is 5. So all these entries are equal entries. So all the entries, these entries are equal. So we need to find dimension of this space Hn. So Hn is a collection of matrix containing this with this property, that is Aij equals to ARS whenever I plus j equal to R plus S. So in this, first A11 is independent position. This is one position. A12, consider this is a independent position, but this is dependent position. Same value here. A13 is independent position. Consider this is independent position. Then all the values are same. A14, consider this is an independent position. So remaining all the values are dependent. So A14 5 means A23 also 5. All the values are 5. Up last entry A1n is independent position. So row there are n entries. Independent position. We can take this is independent position. But remaining values are this 2 dependent, this 3 dependent, this 4 dependent. In the second row, only the A2n. This only one entry is independent. So only one entry independent. Remaining entries are same with this. In third row, A3n, this only one entry independent position. Remaining entries are A2n, 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 this values. In the fourth entry, A4n only the independent position. So remaining dependent positions. So up to all the, in each row, only one element. So in the first row, we can consider all the n entries. So number of independent entries. In first row, totally n elements. Next, second row, one element. Third row, one element. Fourth row, one element. So up to how many rows we have? N minus 1. So totally n minus 1 rows as independent position. Okay, now we have n plus 1 plus 1 plus 1, n minus 1 times. So totally n minus 1 times 1. So this is n plus n minus 1, 2n minus 1 independent position. So dimension of Hn, set of all matrices with this property is 2n minus 1. The dimension is 2n minus 1. So answer is D, 2n minus 1. So we need to find the number of independent positions. For some problems, they will give some different conditions. When the diagonal entries, suppose Aij equals to Aji, or I plus j equal to j plus I, or different condition. For this condition, number of independent positions. First row, all the entries are independent. Consider this is independent. Then each row, the last entry only independent position. So there are n minus 1 entries. So n plus n minus 1 entries. So this is 2n minus 1. Okay, the dimension is 2n minus 1. Now the next problem. Okay, let A be a 3 by 3 matrix with real entries with determinant of A is 6 and trace of A equal to 0. And extra condition, determinant of A plus I equal to 0, where I denote the 3 by 3 identity matrix, then the eigenvalues of A are. So using this condition, we need to find the eigenvalues of A. Here, A is a 3 by 3 matrix. We know that here, A is a 3 by 3 matrix. Determinant of A equals to 6 and trace of A is 0. And determinant of A plus I equal to 0. These three conditions given. Okay, so we need to find the eigenvalues of A. It's a 3 by 3 matrix. It has 3 eigenvalues. So consider the eigenvalues are lambda 1, lambda 2, lambda 3. So this is lambda 1, 2, lambda 3. Consider this lambda 1, lambda 2, lambda 3 are the eigenvalues. So this condition implies determinant. What is the relation between the eigenvalues and the determinant? Product of the eigenvalue equals to determinant of the matrix. So lambda 1, lambda 2, lambda 3. Product of the eigenvalues equals to 6. Next, trace of A equals to 0, the given condition. Trace and eigenvalues relation. Sum of the eigenvalue equals to trace. So lambda 1 plus lambda 2 plus lambda 3 equals to 0. Determinant of A plus I. So what is the determinant of A plus I here? If lambda is the eigenvalue of A, then lambda plus 1 is the eigenvalue of A plus I. Already we check one example. If lambda is the eigenvalue of A, then lambda power n is the eigenvalue of A power n. This is one property. Now lambda is the eigenvalue of A, then plus 1 is the eigenvalue of A plus I. So this determinant of A plus I is 0. So lambda 1, lambda 2, lambda 3 are the eigenvalues of A. Then lambda 1 plus 1, lambda 2 plus 1, lambda 3 plus 1 are the eigenvalues of A plus I. So determinant of A plus I is 0. So we have another property, lambda 1 plus 1 multiplied by lambda 1 plus 1 multiplied with, sorry, this is lambda 2, lambda 3 plus 1 equals to 0. We have 3 equations. 1, 2, 3, 3 equations. Okay, now they given the eigenvalues. Which eigenvalue satisfying this all the property? Then that are the eigenvalues. Okay, first one, minus 1, 2, 3. Check minus 1, 2, 3. Product value is 6. But minus 1, 2, 3. This product is minus 1 into 2 into 3 is minus, but 6. This is not equal to 6. So first one is not eigenvalue of A. Second one, minus 1, 2, minus 3. The product value is, what is the product? Minus 1, 2, minus 3. The product value is What is the product value? Okay, this is 6. 6 equals to first equation satisfied. But sum of the lambda 1, lambda 2, lambda 3 value is 0. So sum of the value -1 plus 2 minus 3 is non-zero. So second equation not satisfied. So this is also not an eigenvalue. For the option C, 1, 2, minus 3. Check this condition. Product value 1, 2, 3, minus 6. Again, the first equation not satisfied. This is also not true. So fourth option, -1, -2, 3. So -1, -2, 3. This is the eigenvalue of A. Its eigenvalue of A means sum of the eigenvalue is 0. -1, -2 plus 3 is 0. So second equation satisfied. Product of the eigenvalue is 6. So minus plus 2 into 3 is 6. So first equation satisfied. This determinant is 0. So what is the eigenvalue of A plus I? If you add one element from this, -1 plus 1, 0. -2 plus 1 is -1. 3 plus 1 is 4. So 0, -1, 4 are the eigenvalues of A plus I. But our condition is determinant of A plus I is 0. Here 0 is the eigenvalue. So determinant is 0. So all the conditions satisfied. So answer D. This is the eigenvalue of A. -1, -2, 3 is the eigenvalue of the matrix A. So this is also simple problem. Using the determinant trace only, we can identify the eigenvalue. Okay, next. Suppose this is a given matrix. A is a matrix, 3 by 3 matrix. As certain complex number, lambda not equal to 0, an eigenvalue. Which of the following numbers must be an eigenvalue of A? Okay, A is a given matrix, 3 by 3 matrix. Then which it has lambda not equal to 0, non-zero eigenvalue. It has one non-zero eigenvalue. Then which of the following is an eigenvalue? Lambda plus 20, lambda minus 20, 20 minus lambda minus 20. Okay. Again, it's a 3 by 3 matrix. It has 3 eigenvalues. Consider lambda 1, lambda 2, lambda 3. These are the eigenvalues of A. We have the condition. Sum of the eigenvalue, lambda 1 plus lambda 2 plus lambda 3 equals to sum of the eigenvalue. This is trace of A. So trace of A. What is the trace of A? 40, 30, minus 50. So if you are adding 70 minus 50, 20. So trace of A is 20. Next, lambda 1, lambda 2, lambda 3 equals to determinant of A. What is here determinant of A? We have to calculate the determinant, but this is given numbers are very 40 minus 29 minus 11 minus 18, 30 minus 12, 26, 24 minus 50. Sorry. So this is a given matrix A. Just add the row elements. Add all the columns. What will you get here? This is 40. 40 minus 29 minus 11, 0. Minus 18 minus 12, 30 is 0. 26, 24 minus 50 is 0. You can make one entry is 0. So you can make one entry is 0, 0, 0. So determinant is 0. So determinant of A is 0. So we have lambda 1, lambda 2, lambda 3 equals to 20. Product of the eigenvalue is 0. So product of the eigenvalue 0 means at least one eigenvalue must be 0. So I am taking lambda 1 equal to 0. At least one eigenvalue, maybe lambda 1, lambda 3. We have 3 eigenvalue. Determinant 0 means non-zero element, product of non-zero elements, non-zero in a field. So at least one eigenvalue must be 0. I am considering lambda 1 equal to 0. So now we have lambda 1 is 0 means lambda 2 plus lambda 3 equals to 20. Lambda 2 equals to 20 minus lambda 3, or lambda 3 equals to 20 minus lambda 2. We have this property. So in this they given lambda equals to 20 minus lambda. So 20 minus lambda, this is correct option. C, 20 minus lambda is the eigenvalue. Suppose this is a 3 by 3 matrix. It has lambda is non-zero value. Then which of the following is an eigenvalue? So this is determinant is 0. So it has at least one eigenvalue 0. Need not be all the eigenvalues 0. At least one eigenvalue 0 means the determinant is 0. So I am taking lambda 1 is 0. Using this trace value, lambda 1 plus lambda 2 plus lambda 3. So lambda 3 equals to 20 minus lambda. So option C is correct. Okay, next. The determinant of the matrix. Okay, this is 3, 4, 6, 6 cross 6 matrix, 6 by 6 matrix. This is also a simple one. Okay, how to find the determinant? Cofactor matrix up to 3 by 3 matrix we can do using cofactor matrix. 4 by 4 also we can do, but all the entries are here. 0 means we can use cofactor matrix method. All the entries are 0. So we can use some elementary operations. So first row, this is 1 0 0 0 0 2. Second row 0 1 0 0 2 0. I'm making this matrix as a upper triangular matrix. So we need to make this 2 2 2 is 0. That is enough. 2 we need to change 0. This 2 I have to make 2 0. These 3 entries we need to change 0. So how to change the remaining? This is 0 0 1 2 0 0. Okay, how to make this is 0? Just multiplying with entry. Okay, this multiplying with the minus 2 and adding fourth row. Okay, R4. So R3 multiplying minus 2 plus R4, then it becomes 0. This entry 2 in, minus 2 into 1 is minus 2. Minus 2 plus 2 is 0. So this is 0 0 0. It becomes minus 4 plus 1 minus 3. Sorry, this is okay. 1 minute. Okay, now 0 0 0. This is minus 3 0 0. Next we need to make this 2 is 0. So use this minus 2 multiplying R2 plus just add R power 5, then it becomes 0. This minus 1 into minus 2 plus 2 is 0. So it becomes 0 0 0 0 minus 3. This is 2 minus 2 into 2 minus 4 plus 1 is minus 3 0. Next last entry we need to make this entry 0. So use the first row. So this is minus 2 multiplying R1 plus R6, then it becomes 0 0 0 0 0. This is minus 2 into minus 2 minus 4 plus 1 is minus 3. Okay, we need to find the determinant of this matrix. Determinant of A. Determinant of A means product of the eigenvalues. So this is an upper triangular matrix. In upper triangular matrix, diagonal entries are the eigenvalues. So eigenvalues are 1 1 1 minus 3 minus 3 minus 3 values. Then take the product of eigenvalues. This product is minus 27. So determinant of this matrix is minus 27. So C is the correct answer. So just to find the eigenvalues, then this is a very simple question. This is also asked in CSIR question. Very simple one. Okay, next we have to check subspace. So we know the definition of vector space. So subspace criteria. So a subset W in Rn is a subspace of Rn if and only if the following 3 conditions hold. So first condition is 0 must belongs to the subspace. W is a subspace of a vector space V. Then W must contain a 0 vector. Second condition, x plus y belongs to W for every x comma y belongs to W. Third one, if x belongs to W and C belongs to R means then Cx belongs to W. Combine these 2 conditions. We can write alpha x plus y belongs to R. Here then, sorry, not R, W. Combine these 2 conditions. X comma y belongs to W means x plus y belongs to W. If x belongs to W, C belongs to R means Cx belongs to W. So I'm taking C here just alpha. So alpha x plus y belongs to W. This only one condition is enough to check. W is a subspace. 0 vector must belongs to the W. Then satisfying this condition, then we can say W is a subspace of a vector space. Okay. Next question. Let M be the vector space of all 3 by 3 real matrix and let A is a matrix 2 1 0 2 0 2 0 0 0 3. This is a matrix given. Okay, this is a non-zero matrix. Sorry, non-singular matrix. Eigenvalue is 2 2 3. So determinant is non-zero. It's a non-singular matrix. Non-singular or invertible matrix given. Which of the following spaces of M? Here M is a vector space of all 3 by 3 real matrices. It's a vector space. This is a we can check collection of all matrices with real entries. Collection of all 3 by 3 matrices with real entries form a vector space. Okay, now W1. W1 is a collection of X belongs to M such that XA equals to AX. That is, all the matrix in M commute with this matrix A. AXA equals to AX. So collection of all the 3 by 3 matrix which commutes with the matrix A. This is a collection. We have to check this collection is a subspace or not. So subspace means we have to check X comma Y belongs to M, then alpha belongs to R. We have to check alpha X plus Y belongs to M. If we satisfy this condition means it is enough. Okay, 0 must be belongs to, since 0 vector, suppose X is 0, this is capital X. 0 matrix commutes with A. 0 matrix multiplied with A is same as A matrix multiplied with 0. So 0 matrix belongs to this set. We have to check remaining this condition. Suppose x1, x2 belongs to W. We have to check alpha x1 plus x2 belongs to W. We need to show that alpha x1 plus alpha x2 belongs to W. Okay, x1 belongs to W means x1a equals to ax1. This is commutes with A. So x1a equals to ax1. x2 belongs to W1. x2 belongs to W1 means x2a equals to ax2. And satisfying this condition, xa equals to ax, it commutes with this matrix. Okay, this implies alpha x1 plus x2 into A. We have to check this element commutes with A or not. So alpha x1 plus x2 into A equals to alpha x1a plus x2a. From this is alpha x1a same as ax1. So ax1 plus x2a same as ax2. This is scalar multiple. So a alpha x1 plus ax2. I'm taking A common. So alpha x1 plus x2. So LHS we have alpha x1 plus x2. So into A. So alpha x1 plus x2 commutes with A. So this implies alpha x1 plus x2 belongs to W1. So W1 is a subspace. Okay, next. Second, W2. Check W2. W2 is a set of all matrix satisfying X plus A equals to A plus X. So commutes with addition, under addition. So this is obvious. X plus A equals to A plus X. So 0 matrix belongs to this W2. Since 0 matrix with A is same as A plus 0 matrix. So 0 matrix belongs to W2. So 0 belongs to W2. We have to check remaining this condition. If x1 belongs to W2 means x1 plus A equals to A plus x1. Next, x2. x2 belongs to W2 means x2 plus A equals to A plus x2. Using this condition, we can prove easily. That is alpha x1 plus x2 A equals to A plus alpha x1 plus x2. We have to verify this LHS equals to RHS. This is equivalent to this value. So this is obvious here. Alpha x1 plus x2 plus A. Here x2 plus A is A plus x2. We can interchange this. You will get this result. A plus. This is addition. In addition, A plus B is same as B plus A. We can interchange this. We can get this is equal. This is just addition. So this implies alpha x1 plus x2 belongs to W2. 0 vector also belongs to this set. So W2 is a subspace of M. Now we have to check trace of AX, collection of matrix, trace of AX. That is, A is a matrix 2 1 0 0 2 0 0 0 3. Collection of this trace of AX equal to 0. This matrix form a vector space or not? Okay, now we'll check W3. So W3 is a collection of x belongs to M. Trace of AX equals to 0. 0, first I have to check 0 matrix belongs to this set. X belong, suppose consider X equal to 0 matrix. X is a 0 matrix means 0, 0, 0, 0, 0. 0 matrix. 0 matrix multiplied with A is, it's a non-zero matrix, you will get 0. So trace of this value is 0. So 0 matrix belongs to W3. So we have to check remaining. If x1 comma x2 belongs to W3, we need to prove alpha x1 plus x2 belongs to W3. If x1 belongs to W3 means trace of ax1 equal to 0. Similarly, if x2 belongs to W3 means trace of ax2 equal to 0. Okay, now we have to check trace of alpha x1 plus x2. Trace b equals to trace of a plus trace of b. So trace of alpha x1 plus trace of x2. Trace of a plus b equals to trace of a plus trace of b. Here alpha, trace of, I'm sorry, here ax1. Alpha, the condition is not correct. We have to check. What is we have to check? Trace of ax equal to 0. x1, x2 belongs to W3 means we have to check trace of alpha ax1 plus ax2 equal to 0. We have to check this condition. So trace of alpha ax1 plus ax2 equals to trace of a plus b equal to trace of a plus trace of b. So this is trace of alpha ax1 plus trace of ax2. Alpha is constant, so alpha trace of ax1 plus trace of ax2. We have alpha trace of ax1 is 0. Trace of ax2 is 0. So this is 0. So alpha ax1 plus ax2 trace is 0. This implies this is belongs to W3. Hence W3 is also a subspace. Now fourth one. What is fourth one? So third one also a subspace. Subspace means I have to check this two condition. 0 vector belongs to the set and alpha x plus y belongs to W. Or we can separately we have to check A is 0 vector belongs to the subspace that subset. X comma y belongs to W means that some value belongs to W. That scalar multiple also belongs to W. We have to check this three condition. I'm checking alpha x plus y directly. I'm combining these two conditions. First, I have to check 0 belongs to the set or not. If 0 belongs to the set means check the second conditions. Okay. So here A, B, C are subspaces. Now what about fourth one? Determinant of Ax equal to 0. So this is fourth one. What is fourth one? Already I written. Okay. Fourth one, W4. W4 equals to x belongs to M. That is determinant of Ax equal to 0. I'm collecting determinant of Ax is 0. So what is the collection here? We have to check. Without checking also we can answer here. How to check? We have a property determinant of A plus B equals to determinant of A plus determinant of B. This is not equal. Determinant of A plus B not equals to determinant of B. Using this property, we can check the condition is not satisfied. But before that, what is this collection says? Here A is our matrix. The eigenvalues of A are 2, 2, 3. This eigenvalues 2, 2, 3. Product of is 2 into 2, 4, 4 into 3, 12. Determinant is non-zero, so it's a non-singular, invertible matrix. But determinant of Ax is 0. Determinant of Ax equal to 0 means determinant of det of AB equals to det of A into det of B. So determinant of A is non-zero, but this implies determinant of Ax is 0 implies determinant of x must be 0. That is, we are collecting a singular matrices. In set of all 3 by 3 matrices, we are collecting a singular matrices. Singular matrices. We are collecting a singular matrices. That is a fourth collection. So the fourth collection is nothing but set of all singular matrices. in the vector space. M is a vector space of all 3 by 3 real matrices. We are collecting a singular matrices. Singular matrices not form a subspace, not a subspace. We know that it's not a subspace. So no need to check this condition. If you check this condition also not satisfied, because determinant of A plus B not equals to determinant of A plus determinant of B. We know that singular matrices, collection of singular matrices not form a vector subspace. So fourth one is not a subspace. So A, B, C are subspace. Fourth one not a subspace. Now we'll go to next example. Okay. Diagonalizable. Already in diagonalizable, we did one example. Again, one example we missed. That is geometric multiplicity. Using geometric multiplicity, algebraic multiplicity equal to geometric multiplicity means the matrix is diagonalizable. But this is equivalent to some other condition. Some places this is very easy to check. The matrix A is diagonalizable or not. That is, number of linearly independent eigenvalues associated with an eigenvalue is geometric multiplicity. This is a definition. Number of linearly independent eigenvalues associated with an eigenvalue. This is also a dimension of the eigenspace. Dimension of the eigenspace is also a geometric multiplicity. Also equal to the dimension of the null space of A minus lambda I. That is geometric multiplicity. We can use this is also for some problems. Geometric multiplicity equals to dimension of null space of A minus lambda I. This is equivalent to geometric multiplicity. Or we can check this condition also. Number of linearly independent eigenvalues associated with a given eigenvalue. For each eigenvalue, we have to check number of linearly independent eigenvectors. Okay, this is not eigenvalue, eigenvector. Number of linearly independent eigenvector. This is typing mistake. Okay, number of linearly independent eigenvectors associated with an eigenvalue. So number of linearly independent eigenvectors same as algebraic multiplicity means the matrix is diagonalizable. Okay, here we need to calculate. Already we did using this number of linearly independent eigenvectors. Now we'll check using dimension of the null space of A minus lambda I. Again, this is upper triangular matrix. So eigenvalues are 1, 1, 4 eigenvalues. Okay, for algebraic multiplicity 1. So geometric multiplicity 1. So no need to check for 4. Lambda equals to 4. No need to check. For lambda equals to 1. Algebraic multiplicity 2. This is 2 times repeated. Algebraic multiplicity is 2. We have to check geometric multiplicity. So we know how to check number of linearly independent eigenvectors for this eigenvalue 2. Now we'll use this condition here. That is dimension of the null space of A minus lambda I. Okay, here null space of A minus lambda I. This is null space of A minus lambda I. This is A 110011004. Lambda value is 1. So subtracting 1, you will get 1 minus 1 0, 1 0, next 0, 1 minus 1 is 0, 1 0. This is 3. So we need to find the dimension of this null space. That is dimension of null space of this value. So dimension of null space of this matrix 0 1 0 0 0 1 0 0 3. This is dimension of null space of, we can make this is 0 easily, multiplying this minus 3 and adding this 3 with third row. So it becomes 0 1 0 0 0 1 0 0 0. Just I'm multiplying this is minus 3 and adding the third row. I'm getting 0 0 0. Now this is linearly independent vector 0 1 0 0 0 1. So we cannot make this is 0. So null dimension of the null space only 1 0 row. This is independent. So 1 dimension of the null space of this matrix is 1. So this is equivalent to geometric multiplicity 1. But we have the algebraic multiplicity 2. So algebraic multiplicity not equals to geometric multiplicity. So this matrix is not diagonalizable. So diagonalizability using this condition also we can check. Some cases this is very easy. That is null space of dimension of the null space of A minus lambda I. This is also equivalent to geometric multiplicity. Okay. So this is not diagonalizable. Next. We have 1250. Okay, we have 2 more questions. We'll finish soon. Okay. P suffix a of x denotes the characteristic polynomial of a matrix A. Then which of the matrices P a of x minus P a inverse of x is constant? So we have to check here. This is a characteristic polynomial of A. So P a of x, it's a characteristic polynomial of a matrix A. P a inverse of x is a characteristic polynomial of a matrix A inverse. So how to find the characteristic polynomial? Find the determinant of, that is determinant of A minus xi. Here in terms of x, we need to find in terms of x. So determinant of A minus xi. So Pax, I'm directly written here, x square minus trace of A into x plus determinant of A. You will get this. Suppose if you take, consider A equals to A, B, C, D. I'm taking this matrix, 2 by 2 matrix with real entries. We need to check only real entries. So I'm considering the real entries. No need to denote A is real entries or complex entries. But our options 3, 3, 2, 4, all the entries are real entries. So I'm taking A, B, C, D. A, B, C, D are real entries. So I'm taking a determinant of A minus xi equal to 0. This is characteristic polynomial. Substitute this, you will get x square minus trace of A into x plus trace of A. You will get this only. This is basic definition. It's a quadratic polynomial. In quadratic equation, x square minus trace of A, sum of the eigenvalues plus product of the eigenvalue, determinant of A. You will get this. Okay, next. P A inverse x. A inverse means determinant of A not equal to 0. Then not 0 means we can find A inverse. What is A inverse? 1 by AD minus BC, DC minus B minus C. Okay, this is 2 by 2 matrix. Inverse exists. Suppose it is determinant non-zero means inverse exists. So P A inverse of x, its characteristic polynomial is x square minus trace of A inverse into x plus determinant of A inverse. Get this. Okay. Okay, now we have A equals to, A is a matrix A, B, C, D. A inverse is 1 by AD minus BC. This is D, A minus B minus C. Okay, this is A inverse. We have A inverse. Now we need to check PA of x minus PA inverse of x. So PA of x minus PA inverse of x. What is this here? If you subtract this, it will be cancelled. X square cancel. If you subtract, it becomes plus. So trace of A inverse x minus trace of A plus, after subtracting, determinant of A, det of A minus determinant of A inverse. You will get this. This is PA of x minus PA inverse. Here x is common. This is x. So x take outside. So trace of A inverse minus trace of A plus determinant of A minus determinant of A inverse. So this will be constant. When this value is constant, RHS, we have constant. When it becomes constant, this we have x coefficient, so it becomes 0. When trace of A inverse minus trace of A is 0, then RHS is constant value. This determinant of A is constant, determinant of A inverse is constant. So this is only the polynomial in x, that is x multiplied with this value. So this becomes a constant, means trace of A inverse minus trace of A equal to 0. This is 0 means x, there is no x term, only constant term. So trace of A inverse minus trace of A equal to 0. This implies trace of A inverse equals to trace of A. So A inverse same trace means its value is 0. So what is the trace of A inverse? We have A inverse. Its trace is D by AD minus BC plus A by AD minus BC. This is the trace of A inverse. This is equivalent to trace of A is A plus D. Okay, here denominator is same. So a plus d. Okay, now we have numerator a plus d by denominator ad minus bc. A plus d by ad minus bc. RHS we have a plus d. Here, suppose a plus d not equal to 0 means we can divide both side by a plus d. This is not always possible. Suppose a plus d is non-zero means we can divide both side a plus d. It becomes 1 by ad minus bc equals to 1. Ad minus bc is what? Ad minus this determinant of a equals to 1. This implies determinant of a equals to 1. So determinant of a equals to 1 means this is constant. That is p a of x minus p a inverse of x is constant means trace of a inverse equals to trace of a. And also if you assume a plus d is non-zero means we have determinant of a equals to 1. So we have 4 conditions. First one 3 3 2 4. What is it here? This we have to check this condition. A plus d non-zero, that is trace is non-zero. 3 plus 4 trace is non-zero. 4 plus 3 non-zero, 3 plus 3 non-zero, 2 plus 4 non-zero. So non-zero. So we can check determinant of A is 1 or not. So what is the determinant here? Determinant of this matrix is 9 minus 4 not equals to 1. 9 minus 6 not equals to 1. This is 12 minus 6 not equals to 1. 3 3 9, 9 minus 8 equals to 1. Here this is 2 into 2, 8 minus 9 minus 1. So not equals to 1. The matrix C matrix satisfying the condition. That is determinant of A equals to 1 means P A of x minus P A inverse of x is constant. So only the C matrix satisfying the condition. So C is the correct answer. Okay. Now next question. Okay, I think this is the last question. We'll finish 5 minutes. Okay. Okay, this is also very simple one. A is a Aij be the 3 by 3 complex matrix. Identify the correct statements. Okay, 3 by 3 matrix. So what is 3 by 3 complex entries? So complex entries, I'm taking A11, A12, A13, A21, A22, A23, A31, A32, A33. It's a 3 by 3 complex entry. We have to check determinant of minus 1 power I plus j Aij equals to determinant of A. So first option A, we'll check this. Determinant of minus 1 power I plus j Aij equals to. So determinant of I plus j, this is 1 plus 1. 1 plus 1 is 2. So this is minus 1. This each coordinate place 1 1 1 plus 1 is 2. That is I plus j, where ij is the place value, first row, first column. So 1 plus 1 is 2, minus 1 power 2, A11. This is minus 1 power 1 plus 2 is 3, A12. This is minus 1 power 1 plus 3 is 4, A13. Second row, minus 1 power 2 plus 1 is 3. So 3, A21. This is minus 1 power 2 plus 2 is 4, A12. Minus 1 power 2 plus 3 is 5. This is A23. Last row, minus 1 power 3 plus 1 is 4, A31. Minus 3 plus 2 is 5. This is A32. Minus 1 power 3 plus 3 is 6, A23. Okay, now using the determinant property, minus 1 square, first row minus 1 square common. Here minus 1 power 3 is common. And third row minus 1 power 4 is common. So taking outside minus 1 square, minus 1 power 3, minus 1 power 4. So remaining is A11 minus 1 power 1. Here minus 1 square, A13. Here 2 minus 1 power 2 is out common. So this is minus 1 power 3 is common. So remaining A21 minus 1 power 1, A12. This is A12. This is A22. A22. Sorry, this is minus 1 power 2, A13, 2, 3. In the third row, minus 1 power 4 is common. Remaining A31, minus 1 power 1, A32, minus 1 power 2, A33. Okay, now again In column wise, minus 1 power 1 is common. Here minus 1 power 2 is common. So if you take outside minus 1 square, minus 1 cube, minus 1 power 4. In the second column, minus 1 power 1 is common. Here minus 1 power 2 is common. So remaining just A11, A12, A13, just a matrix A. So base same, so add the powers 5, 9, 10, 12. So minus 1 power 12 is plus 1. So this is determinant of A. So determinant of A. So determinant of minus 1 power I plus j, Aij equals to determinant of A. So first option is correct. Second option, same, LHS is same, minus determinant of A. This is not correct. We are getting determinant of A. This value is determinant of A. Now we have to check option C. Determinant of minus 1 power I plus j. Just replacing minus 1 in place of square root of minus 1. So square root of minus 1 means square root of minus 1 equals to I. Just replacing I. If you replacing I, all the calculations are same. You can take outside minus 1 instead of I power 2, I power 3. So you will get I power 2 plus 3, 5, 9, 10, 12. I power 12 into determinant of A. What is the value of I power 12? I power 4 is 1. So I power 12 is 1. So determinant of A. So again, determinant of this value equals to determinant of A. So this is not correct. So same calculation. In the place of minus 1 power I plus j, we have to replace square root of minus 1 I plus j. So all the calculations are same. You will get in last step I power 12 into determinant of A for the third option. So this is also equivalent to determinant of A. So fourth option is not correct. So first one is true. This is simple calculation. No need any properties. Okay, thank you. I will stop here.
Thank you, sir, for your wonderful explanation. Sir, there are 2 questions, sir, from student side. Shall I post it?
1 minute, ma'am.
Yes.
Yes, ma'am. 1 minute, ma'am. Yes, ma'am. Questions, ma'am?
Yes, sir. What is algebraic multiplicity and geometric multiplicity in 8th question?
In 8th question, I explained, ma'am, algebraic
In 8th
multiplicity.
question.
Number of eigenvalues, how many times repeated, given a matrix, how many eigenvalues, how many times repeated, that is algebraic multiplicity. Geometric multiplicity means number of linearly independent eigenvectors corresponding to the eigenvalue, that is geometric multiplicity. So rendu problem explain pannirukkom, ma'am.
Okay, sir. Okay, so one more question, sir.
Okay, ma'am.
Can you explain 7th question again?
Can you explain 7th question again? 1 minute, ma'am. I don't know what is the 7th question.
Yes, sir. Yes, sir.
7th question. Okay, this is the 7th question. Is it visible, ma'am?
Yes, sir.
Okay, 2 minutes, ma'am.
Slide show, sir.
Okay, ma'am. From the current slide, okay. Okay, this is I did P of x. This is a given polynomial P of x, non-constant polynomial of degree n greater than or equals to 1. So they are defining Q of x and R of x. So I am finding using P of x. This is P of x. I calculated Q of x. Q of x is defined by 0 to x P of t dt. I am getting the answer a0 x plus a1 x square by 2, a3 x 3 by 3 plus a power n x power n plus 1 by n plus 1 after substituting the upper limit and lower limit. So this is my Q of x. Next, I need to calculate the R of x. R of x is just derivative of the polynomial P of x. I am taking the derivative of this P of x. So a0 is 0. So a1x is a1. a2 x square is 2a2x plus a3. Just differentiate, you will get the final degree is x power n minus 1. This is enough. Okay, here Q of x. If you want, write explicitly all the terms Q of x and R of x. Here Q of x is polynomial of degree n plus 1. Q of x is a polynomial of degree n minus 1. The degree is different. So it cannot be written as linear combination of some value alpha. That is, R of x cannot be written as some constant multiple of Q of x. So this is not linearly dependent. So this is not correct. Answer B is not correct. This is linearly dependent is not correct. Since we cannot write R of x is a just a constant multiple of q of x. Since the degree is different, n plus 1, q is degree n plus 1, R is degree n minus 1. So cannot be written as constant multiple. So answer B is not correct. So it is linearly independent. So these two q of x, the polynomial q of x and R of x are linearly independent in V. Next, x power n belongs to the linear span. Linear span means, okay, I cannot erase this. Okay, so linear span, x power n. Linear span means x power n is a linear span of q of x and R of x. That is, we can write some alpha times plus beta times R of x. Then x power n belongs to the linear span of this. So q of x and R of x linear span. It's a linear span means alpha times q of x plus beta times R of x. Collection of this is a linear span of q of x and R of x. We have to check x power n belongs to this collection. X power n plus 1 belongs to this collection. We proved thus here alpha, at least alpha not equal to 0 or beta not equal to 0. Both the values 0 means every element belongs to this span. So our definition, at least one alpha or beta is non-zero. We proved x power n does not belongs to this collection. X power n plus 1 also does not belongs to this collection. That is, the collection is span of q of x and R of x. This calculation part I did fully. Just I gave a hint only. If is comparing the coefficient x power n plus 1 and constant term coefficient. This is easy one. Alpha value, beta value also 0. For the same calculation for x power n plus 1, you will get alpha value 0, beta value 0. Both the values are 0. So x power n does not belongs to the linear span of q and R. X power n plus 1 also does not belongs to the linear span of q and R. Okay, ma'am.
That's all, sir. That's all. Okay. Questions are over, sir. Okay, thank you, sir. Thank you, sir.
Okay, ma'am. Thank you, ma'am.
Okay, sir. Now I...
Thank you for taking your time to prepare for us such an extraordinary, wonderful presentation, sir. That was flawless. Thank you, sir. Thanks to Professor Venkatramanan, Head PG and Research Department of Mathematics, for organizing this C4 workshop. Coming week, no C4 class. Our next session will be held on 21/11/2020 at 6 p.m.